Recording in progress.
Right. So, good evening, student. Let me start again. One student, please confirm the hearing of my voice and visibility of my screen. So, one student, please confirm.
We can hear you, sir.
Okay, right. Thank you very much. Right. So, we have discussed the momentum impulse theory, or even we can say impulse momentum theory. So, what happened here that you have an impulse. So impulse is defined by force into time, which is equal to change of momentum. So it means that somebody is having a velocity, and that velocity is changed because of application of force due to a certain time period. So you have impulse, and this particular impulse is equal to change of momentum. Now, important thing is, so if you have impulse, what you have to understand is that you have a change in momentum. කියන්නේ ඔයාගාව ඔයා ෆෝස් එකක් ඇප්ලයි කරනවා නම් යම් කිසි කාලයකදී එතන මොමන්ටම් චේන්ජ් එකක් තියෙනවා. So what happen if you don't have a impulse එකක් නැහැ. impulse එකක් නැති වුණාම මොකද වෙන්නේ? මොකද්ද වෙන්න පුළුවන්? momentum change එකක් නැහැ. It means that the final momentum is equal to the initial momentum. So momentum of object will not change if you don't have a force. There's a situation that you have a force, but there is no unequal force. මොකක්ද අසන්තුලිත බලයක් නැහැ. තියෙන එක සන්තුලිත බලයක් වෙන්න පුළුවන්. net force එක 0 වෙලා තියෙනවා. In that case, you have no change of momentum. It means that initial momentum is equal to the final momentum. So in that kind of situation, we just say the momentum is conserved here. මොකද්ද වෙලා තියෙන්නේ? momentum එක conserved වෙලා. momentum එක conserved වෙලා if you do not have unbalanced force. balance නැති force එකක් නිසා force එකක් නැහැ. ඒකෙන් momentum එක conserved වෙලා. So if there is a system with the momentum conserved, we call this one as an isolated system. For an example, what happened here? Now you have object coming to this direction, and then another object is moving to this direction. If this velocity is u1, and if this velocity is u2, if the u2 velocity is greater than u1, you have a collision. මේක නිසා collision එකක් වෙනවා. So if you have a collision, and this type of collision will occur. But in this collision, you have a force to this direction, and then force to this direction, but this is balanced. Finally, net force is equal to 0. So net force is equal to 0 means there's no impulse. Net force එකක් නැහැ. impulse එකක් නැහැ. So in this particular system, we can say momentum is conserved. So once it hit, and then it will move to a new velocities. මේගොල්ලෝ දැන් අලුත් velocities වලින් යයි මෙහෙම. වැඩිලා ඉවර වෙලා. So we can say this is V1 and this is V2. And we can write in this particular situation, momentum is conserved. It means that initial momentum is equal to the final momentum. So So this type of system is so-called isolated system. So in that case, mu2 plus, we can say this is m1 and m2. අපි පොඩ්ඩක් mass එක වෙනස් කියලා හිතමු. m1 u2 m2 u1 is equal to m1 v1 plus m2 v2. ඔන්න බලන්න මේ වැඩේ. So momentum is conserved. So in this case, we can say momentum lost by somebody, momentum gained by another one. කවුරු හරි loss කරගන්න momentum එක තව කෙනෙක් අරගෙන තියෙනවා. ඒක තමයි scenario එක. So it's also called conservation of momentum. So no external forces act on a system. The total momentum system will not change. Total momentum of the system will not change. එහෙනම් external forces නැත්නම් තියෙන forces ටික සමතුලිත වෙලා නම් තියෙන්නේ ඒ වගේ system එකක total momentum එක conserved. Total momentum එක will not change. So that is the meaning of the conservation of momentum. නම් අපි conservation of momentum පාඩම ඉගෙන ගමු. ඒක කියන්නේ momentum එක conserved වෙනවා. No external forces act on a system. Total momentum will not change. මෙහෙම system වලට අපි කියනවා isolated system. So I'll give you 2-3 minutes for you to write this one. ගම්‍යතා සංස්ථිතික නියමය. Conservation කියන්නේ සංස්ථිතිකයි කියන එක. ඒ කියන්නේ පෙර සහ පසු කියන අවස්ථාව සමානයි කියන එක. Conservation. The conservation of momentum කියන්නේ ගම්‍යතාවය. එහෙම වුණා අපි කියනවා ගම්‍යතා සංස්ථිතික නියමය කියලා මේක. Right? Is it clear? තේරුණාද? So this is clear for you all. So I'll give you several minutes for you to write. So same time, if you have any question, you can ask. කාට හරි ප්‍රශ්නයක් තියෙනවා නම් දැන් අහන්න පුළුවන්.
Recording stopped. ඔව් ළමයි ප්‍රශ්නයක් අහනවා U2 දැන් මේ U2 වැඩි නිසාද කියලා. ඒක ඇත්ත. මොකද නැත්නම් ඔය පිටිපස්සේ එන කෙනා
ට වදින්න බෑනේ ඉස්සරහ යන කෙනාට. ඒක නිසා තමයි මොකද දැන් ඉස්සරහින් යන කෙනා එමීට යන්න ඕන පිටිපස්සෙන් යන කෙනා හයියෙන් ගිහලා තමයි වදින්න ඕන. ඒක වැද්දාම තමයි එයාට ආපහු මෙහෙම යන්න පුළුවන්. ඒකට යනකොට ඉස්සරහින් යන කෙනා ටිකක් වේගෙන් යනවා පිටිපස්සේ යන කෙනා හිමීට යනවා. ඒක තමයි වෙන්නේ නේද? සාමාන්‍යයෙන් බෝල දෙකක් හිමීට යන්න දීලා ගැහුවාමත් එන්නේ ওই වගේ වැඩක් කියලා. ඒකින්ද තමයි ඒක දාන්නේ. ඒ ළමයි අහනවා මේ මම නිකන් එක්සාම්පල් එකක් පොඩ්ඩක් කරන්නම් බලන්න මේක ඕගොල්ලෝ දන්න එකක්. Let's try to understand this one. So this is happening especially so you have seen this one in films and other things, and this is so called recoil of gun. Then so you all know that weapons such as shotguns and rifles, and these items are working under the basic idea of this conservation of momentum. So in the case of firing, let's say you have a bullet that you have a rifle, and so bullet is coming out of a gun, and so basically we apply huge force, and this is happened by exploding the gunpowder. So due to this gunpowder explosion, it's create large force. Yeah, so in the case of firing, what happened? So we consider initially the bullet and the gun as a one system. So you can say in this particular system, there's no net force on the bullet or gun system. Net force එකක් නැහැ. තියෙන දෙක equal වෙලා තියෙනවා. So we can say the bullet and plus gun, the momentum should be conserved. So ultimately that, let's say this is the gun, and so you have a bullet here, and this particular system you cannot find net force. So initially both are at rest. Then we just apply this part, this lever, and then there's gunpowder explosion, and we have a velocity for this particular bullet. And let's say that the bullet is mv, the mass, and the velocity of the bullet is vb. So this is in this direction. So the initial velocity is 0. Initial momentum is 0. The initially මොකුත් වෙලා නැහැ. So this is happened after the explosion of gunpowder. So then the gun is moving to this direction, and you have another force to the back side. අනිත් පැත්තට force එකක් තියෙනවා. ඒවා මේක එකතු කරන්න ගියොත් වෙන්නේ, so basically the direction is other side. So we put minus. So we have gun and mg, and there's a velocity for gun. This velocity is so-called recoil velocity. අපි මේකට කියනවා recoil velocity, නැත්නම් අපි මේකට සිංහලෙන් කියනවා වාංගු ප්‍රවේගය කියලා. ගන් එක මෙහෙම පස්සට දෙන්නේ මේක නිසා. ඒක තමයි අපේ සාමාන්‍යයෙන් මේ සිස්ටම් එක වෙන්නේ. මේ සමහර වෙලාවට now if somebody did cadeting and they have practiced this one using different gun, and we have air rifles and also some different gun, and they are practicing put the gun on the shoulder එකේ තියලා තමයි වෙඩි තියන්න ගන්න. එතකොට may recoil velocity if it is so large, and ultimately that you have a situation where your shoulder will be dislocated. Shoulder එක යනවා කියලා සමහරලාට වෙනවා ඉස්සර. So this is happening because of that reason. So ultimately that you have to understand that you have to keep this VB very large. මේ VB කියන එක න ගොඩාක් වැඩි වෙන්න ඕන. එහෙම නොත් තමයි මිනිහෙකුට වැදුනා මැරෙන්නේ. Otherwise there is no purpose of using gun. Right? So the bullet cannot go there and touch the person. So bullet has to penetrate through the person. This is the only way that we can attack to a person and the person will die. So you have to penetrate the bullet through the body. So in that case, you need large velocity. And same time, you have to have a very small velocity of VR. Otherwise, that your shoulder will dislocate. So there are several factors involving that one. It means that this part should be large. To large this one, VB should be large. MB should be small. VB large කරගන්න ඕනේ, MB අඩු කරගන්න ඕනේ. So in this case, MG should be large, VR should be small. වාංගු ප්‍රවේගය අඩු වෙන්න ඕනේ. එහෙම කරන්න අපි කරන්නේ බර වැඩි කරනවා ගන්න එකේ. මේ පැත්ත වැඩි කරගන්න. මේ පැත්ත වැඩි කරගන්න we reduce the weight of the bullet. Bullet එකේ බර අඩු කරනවා. එහෙම කරාම velocity එක වැඩි කරගන්න. Right? So normally the bullet, the mass of the bullet is around 10 gram. So gun is around 2 kilogram. This is the weight of the gun. And velocity of the bullet, which is of course around 400 ms minus 1. So VB, which is very large, which is 400 ms minus 1. Sound velocity එකට වඩා වැඩි. It's more than sound velocity. Okay, so calculate the VR value. VR calculate කරලා බලන්න. So this is real scenario, right? So send me the answers of VR, then you can understand. එහෙනම් මම සිංහලෙන් කිව්වා ගන්න එකයි බුලට් එකයි තියෙන සිස්ටම් එකේ net force එක 0. So the initial momentum එක 0 මේ වෙලාවේ. කවුරුත් move වෙන්නේ. ඊට පස්සේ ගන්න එකේ වෙඩි බෙහෙත් explode වුණාම බුලට් එක යනවා move වෙනවා ඉස්සරහට. ගන්න එක යනවා පිටිපස්සට. Because we need the system to conserve the momentum. So if it is moving the same direction, this equation is false. Now the equation is true. Because MB VB equal to MG VR now. So this is the only way that we can get this one. Right? So we can get this particular value. So I have given you the real situation. You can calculate now. So you can calculate and find what is the value of VR. VR වල value එක දැන් පොඩ්ඩක් හොයලා බලන්න කොහොමද value එක වෙන්නේ කියලා. Right.
Recording in progress.
Right. So a lot of students send me the answers, and the answer is 2ms minus 1. So 2ms minus 1, and if you convert this one to kilometers per hours, so which is around, since it is 2ms minus 1, which is around 7 kilometers per hour. So 7 kilometers per hour, you all can understand it's not such a high speed one. So it's mean that you are saved. However, that you have to understand that you have to have a gun which is the weight of 2 kilogram, which is relatively large, and also the bullet size of the bullet is 10 gram. So it should be very small in the case of weight of the bullet, and in the case of weight of the gun, it should be very heavy. So it's normally it's heavy, of course. So you all can understand that it's heavy, right? So let's try to do another question, right? I'm expecting you all to send answers for this thing, right? Mama බලාපොරොත්තු වෙනවා ඔයගොල්ලෝ හැමෝම මේකට answers එවයි කියලා. So hope this is clear. This is recoil velocity. I have given you the idea, and if the velocity is large, then you may get dislocate of your shoulder, and you had to avoid that one, and that is why that we have the bullet with less weight and the gun with high weight, right? Right. So let's try to understand this particular scenario. And so here we have one trolley, right? The trolley is moving with the velocity of 20 ms minus 1, and the weight of mass of this trolley is 8 kilogram. And you can have another trolley which is stationary available. නැවතිලා තියෙන එකක් තියෙනවා. Right? ඒක නැවතිලා තියෙන. So their mass is 4 kilogram. ඔන්න මෙයාගේ mass එක 4 kilogram. එතකොට මෙයා ඉන්නේ නැවතිලා. That is stationary. So velocity is equal 0. So there's a collision. There's a collision. And once collision occur, these trolleys get together. මේ trolley දෙක ඔන්න එකට එකතු වෙනවා මෙහෙම. And moving to this direction. So you need to find this velocity. This is the question. This is very easy, and so I believe you can do this one very simply. So please find the velocity of this particular system which is moving to this direction, right? Hope this is clear. Right. So please try to find this one.
Recording stopped. Recording in progress.
So this is very easy, right? This is very easy, and let's see. So about Tikshana, are you there? Right, no.
Yes, sir.
All right, Tikshana is there. And how about this Sarojani? Sarojani, are you there?
Yes, sir.
Okay, Sarojani, have you done the question?
Yes, sir.
What is the answer?
13.33.
Okay, so how about Tikshana?
Yes, sir.
What is
13.33.
okay? So it's easy, right?
Yes.
Right. So what you have to do is that we have to find the initial momentum. Peragamyatavya. So here it is 20 into 8. So we just consider this direction as positive. And then this one is 4 into 0. Then we have a situation that it's get together and making one system, then 12, and the velocity is moving to this direction. It is positive, then it's 12v. So it's ultimately 160 divided by 12. So as the two students informed, this is around 13 point something. So now you all have certain idea and how to apply conservation of momentum in any case, right? So this is clear for you all, right? Any questions? මොනවාද තියෙනවද ප්‍රශ්න? මොකුත් නැද්ද ප්‍රශ්න? Right, seems to be no. Momentum and this one. Right, so let's learn the other part. අපි ඊළඟ part එක ඉගෙන ගමු. Right. So the final part of classical mechanics, considering these the movement of objects and also the Newton laws and momentum, impulse, and then we have to talk about work and energy, right? Work and energy. So work and energy. So in this case, so normally in the case of concept of work in physics is different with the commonly used in a normal environmental situation. So our everyday language, so we basically say work is related to basically it's muscular effect. So normally we are using our energy, our own energy to do something. So this particular thing is so-called work in normal general usage. However, that so what happened in the case of physics? So in physics, we consider objects. So object is moving, and so to particular situation, once you apply force and you have a certain displacement. So if force can make object to cause any displacement, in this particular situation, we just consider we have work in the case of physics. For physics වල නම් work එකක් වෙන්න force එකක් apply කරලා displacement එකක් වෙන්න ඕන. යම් කිසි දුරක් යන්න ඕන. දුර යන්න ඕන force එක නිසා. force එක නිසා displacement එකක් ඇති වුණාම that is so called work in the case of physics. So physics, you have to have displacement occurred by the force. So we can define the force, and let's say that if you have an object like this, and we are applying force, and then object is moved to this direction until here. If it is D, then we can define the work as F into D. F වැඩි කිරීම D. F multiple by D. So you have to consider the direction here. So work is happened to direction here. And we can get the work particular situation. We have to consider the which direction we are basically do this particular displacement. So in the case of work, as I said, that we defined work as force into displacement. So we have to consider the particular direction. Now this is prime example. So force is happening to this direction, but the displacement occurred in this direction. So we need to get the force applied to this direction. So please do understand that if you have anything, this might be force, this might be velocity, whatever it is, with the angle of certain direction, this is the direction, and if we have angle theta, we basically divide this particular parameter into two ways. අපි සාමාන්‍යයෙන් තිබ්බහම මේක අපි මේ දෙපැත්තට තියෙන forces හොයන්න ඕන. දැන් angle එක theta නම් මේක f නම් if it is f, we define this one as f cos theta. And this is f sin theta. The resultant of f sin theta and f cos theta is equal to f. So here we have a force f to this direction, but our object is moving to this direction. So our work is happened to this direction, and in this direction, we have to get the component of the force, which is f cos theta. And we have to multiply by delta x to find the work to this direction. So f cos theta into delta x is the force. F is the work. So this is the work. F cos theta into delta x. So what happened into this direction? This direction. There's no displacement. So in that case, for that direction, work is zero. Right? So you have to understand this. You need to learn this one carefully. So there's no work to y direction, there's a work for x direction. Of course, there's a force to y direction. This is F sine theta, but there's no displacement. Right? Hope this is clear for you all. So what happened here? Right? So let's talk to Sarojani again. Sarojani.
Yes, sir.
Oh, පුතාට තේරුණාද මේක? Do we have a force? Do we have a work to y direction here? උඩ පැත්තට අපිට work එකක් තියෙනවද?
No, sir.
No, because we don't have displacement to there. උඩ පැත්තට මෙයා move වෙලා නැහැ. Do we have a force to that direction? අපිට මේ පැත්තට force එකක් තියෙනවද උඩ පැත්තට?
No.
උඩ පැත්තට force එකක් තියෙනවද අපිට? Right. Hasaranga, are you there?
No, sir.
Do we have force to y direction? අපිට force එකක් තියෙනවද මේ පැත්තට? මෙහෙම තමයි දැන් force එක apply කරලා තියෙන්නේ. angle එක θ තියෙනවා. අපිට මෙහෙම වුණාම force එකක් තියෙනවද x direction එකට? අපිට මෙහෙම වුණාම force එකක් තියෙනවද y direction එකට? තියෙනවද නැද්ද? So Teekshana, are you there? Anyone can talk here? Alhara or the Kavindu? Kavindu Gayashan?
Yes, sir.
Do we have a force to y direction?
දෙකටම යනවනේ කියන්නේ උඩට යන්නේ
දෙකටම
නැහැ.
දෙකටම යනවා නේද? So if
ඔව්
we
සර්.
have a force like this, we have a component to this direction, that is F cos theta. If you have a force like this, we have a direction force to y direction, that is F sin theta. ඒ වගේ ඔයාලා දැන් මතක තියාගන්න. force එකක් තිබ්බොත් angle එකක් වෙලා අපිට දෙපැත්තටම force දෙකක් තියෙනවා. එයාගේ විභේදන කියලා කියන්නේ අපි ඒවා. එයාලගේ part. ඒ part එක තමයි මේ පැත්තට F sin theta, මේ පැත්තට F cos theta, angle එක theta නම්. හරිද? Is it clear? Right. Is it clear? Okay, good. Right? So some people, some students send me the answer. Right. So here we have a force to y direction. Do we have a displacement to y direction? අපිට displacement එකක් තියෙනවද y direction එකට? No. නේ ඒක නිසා අපිට මේ පැත්තට force එකක් work එකක් නැහැ. අපිට මේ පැත්තට තියෙන. Right? So this is clear for you all. So you can write this one. Right? You can write this particular idea. I'll give you 2-3 minutes. Right. Then let's talk to some students. So let's talk to Pramodya. Pramodya, are you there?
Yes, sir.
Okay. Then how about Sevandi? Right. No. So let's talk to Mudita also. Pramodya and Mudita.
Yes, sir.
Right. So delta x කියන්නේ ගමන් කරපු දුර. That's okay. Right. So we have Pramodya and Mudita. So is it clear for you all? ඔය දෙන්නට මේක පැහැදිලිද?
Oh, sir.
Yes, exactly.
Right. Clear නේද? That's clear. Right. Now let's try to understand something. Right. I'll give you one photograph. Right. So Pramodya, where are you?
I am from Anuradhapura, sir.
Anuradhapura. Right. So what is your school?
Medavachi Central College.
Adavachi Central. Right. And then who is that? The boy? I forget the name.
Mudit, sir.
Mudita. Mudita, where are you?
I am Rathur, sir.
Ratnapura.
Yeah.
Okay. So Mudita, do you know this person?
Archimedes.
Archimedes. How about Pramodya? Pramodya, do you know this person?
I don't know, sir.
Okay. Who knows this person? කවුද දන්නේ මෙයාව?
Atlas.
Atlas. Right. කවුද කිව්වේ?
Sanka.
Okay, Sanka. Sanka, this is Atlas. Right? And Atlas is, of course, so it's a Gero. Gero means යෝධයා කියන එක. And the god කෙනෙක්. So in Greek mythology, one of the Greek Gero is Atlas. And so he is sort of a student of one of the god, so-called Zeus. And then this Zeus asked him to hold the world. Atlas කිව්වා ලොකු වැඩක්. මොකක්ද කිව්වේ? එයාට පොඩි දඬුවමක් දුන්නේ. ඒක ග්‍රීක දේව සභාවේ හිටපු ලොක්කා තමයි ඒ වෙලාවේ සියුස් කියන දෙවියා. එයාට කිව්වා so you have to hold the earth by yourself. ඔයා මේ ලෝකේ ගෝලේ උස්සගෙන ඉන්න ඕනේ. So it's a tremendous work. So sometimes people say that we are getting earthquake because Atlas is moving this particular earth a little bit here and there. So Atlas is doing a great work here. So what I have to know that does Atlas do any work here? අපේ ළමයි දෙන්න කියන්න ඕන මට ඒක ආපු දෙන්න Atlas මෙතෙන්දි work එකක් කරනවද නැද්ද? Right. කවුද ප්‍රමෝද්‍ය කියන්න බලන්න.
No,
No. Why there's no work?
there is no displacement.
Very good. Right? You just keep your Medavachi Central College proud. There's no displacement. Even there's a force. The force is in this direction because of this is very heavy, and ultimately that we have a force to this direction, but there's no displacement. So in this case, we can say that Atlas is not doing any work according to physics. According to physics, Atlas මොකක්වත් කරලා නැහැ. right? So what happened in this particular case? Let's suppose this one. So this is in the case of weight. Let's draw a weight here. අපි හිතමු weight කෙනෙක් මොනවාරි අරන් එනවා. So let's draw a weight here. This is the weight. Restaurant again. So we have some items here. Chicken, glass of whiskey. He's bringing something to this direction. So he's doing this one with great commitment, bringing everything for us when we are ordering. So does the waiter do any work here? මේ waiter මොනවා හරි වැඩක් කරනවාද මෙතන? According to the physics. මොකද කියන්නේ ප්‍රමෝද්‍යා? මේක උස්සන් එනින්ද waiter වැඩක් කරනවාද?
Yes, sir.
Huh?
Yes.
Or he's moving. Now we have a displacement. Does the waiter do a work here?
Yes, sir.
Bringing this one, waiter is not doing any work. Because now the displacement occurring in this direction, but the force is to this direction. Mg is to here. So according to physics, there's no work. But there's a work if you're considering friction force. Friction force එකත් එක්ක ගත්තාම there is a work. Because friction force will occur considering the weight of this one and weight of the particular person. So in the case of friction force, you have a work. But considering the tray, you don't have work here, according to this particular thing. Right? So this sort of funny situation. We have to pay because of that he is moving against the friction. අපි එන සල්ලි ගෙවන්නේ මේක උස්සන් ආවට නෙමෙයි මේකේ බරත් එක්ක ෆ්‍රික්ෂන් එකත් එක්ක ඇවිල්ලා අන්න ඒකට ආවට. එතකොට තමයි ටිප් එකක් එහෙම දෙන්නේ යාට. Right? So you have to tell once you go to the restaurant and saying that I am paying you because not for the bringing these items, we are paying that you have done a work against the friction force. Friction force එකට against මොනවා හරි දෙයක් කරපු ඉඳ තමයි අපි ඔයාට සල්ලි දෙන්නේ කියලා කියන්නේ. Right? Right. So that is in the case of work. So let's try to understand energy. Energy කියන එක පොඩ්ඩක් ඔයාලා බලන්න. Energy. So in the case of energy, we are considering two energies, especially the situation where that some objects are moving upwards. මෙන්න මේ පොඩ උඩ යන කට්ටියගේ energy එක තමයි අපි මෙතෙන්දී පොඩ්ඩක් කතා කරන්නේ. So we have energy so-called kinetic energy. So kinetic energy is defined as half mv squared if the object's velocity is v. Kinetic energy කියලා අපි define කරනවා. So this is the kinetic energy when the object is moving with the velocity v. Right? It's kinetic energy. And on the other hand, we defined another energy, as I said, that is work done against the gravity. And කෙනෙක් උඩ යනකොට gravity එකට against යනකොටත් අපි force එකක් define කරනවා. That is define when we have a force against a displacement. So here the particular one start here and move into here. So we have another energy we define. This is so-called potential energy, which is defined as mgh. So we have a two type of energy. One is kinetic energy. This is half mv squared. The other one is if a mass m at height h, we define this particular energy as potential energy, which is mgh. It's a potential energy. In this type of situation, if somebody is moving through the gravity, please do understand that always potential energy plus kinetic energy is equal. Potential energy plus kinetic energy is equal for anyone. Potential energy and kinetic energy is equal, plus equal. So in that case, we can say that energy is conserved. mgh plus half mv squared is constant if gravity is the only force doing the work. So this is against gravity. එහෙනම් මේ කොතනක හරි හැමතැනම potential energy එකයි kinetic energy එකයි constant. Energy is conserved in this case. So in this case, we define as energy is conserved. ශක්තිය සංස්ථිතිකයි. Gravitational potential energy, kinetic energy. So what happened at the ground level? At the ground level, mgh, h is 0. So there's no gravitational force, it's only kinetic energy. So what happened on the top? Velocity is 0. It's all about mgh. So in the top, we have mgh. Here we have kinetic energy. So this is a scenario. So here we can say that if the gravitational force is the only force, in that case, gravitational potential energy plus kinetic energy is constant. Energy conservation. So we have learned two laws now. One is conservation of momentum. The other one is conservation of energy. ධම්මික සංස්ථිතික නියමය සහ ශක්ති සංස්ථිතික නියමය කියන දෙකම අද අපි ඉගෙන ගන්නවා. Right. Hope this is clear. මොනවාරි ප්‍රශ්නයක් තියෙනවද? ඔයගොල්ලෝ ඕන ප්‍රශ්නයක් අහන්න පුළුවන්. ඒතර මේ part එකෙන් අපේ classical mechanics part එකේ object ගැන කියන part එක ඉවරයි. So next day that we will talk about fluid dynamics, fluid mechanics. ඒකේ අපි පොඩි mechanics part එකක් විතරයි කතා කරන්නේ. So next day we are going to learn about fluid mechanics. So I will do this lecture in Friday, and so I will let you know the time. So basically I have informed to your WhatsApp group. So Friday that I will do. So Friday, do you have lectures? Friday or the lectures තියෙනවද?
කෙමිස්ට්‍රි එකක් තියෙනවා සර් උදේ.
උදේ කීයටද ඒක තියෙන්නේ?
ටයිම් නම් දාලා නැහැ සර් තාම.
හරි.
සාමාන්‍යයෙන් 3 hours වගේ තියෙනවා.
Right. So anyway, that I will start at 8 o'clock and then finish at 9 o'clock, right? Because now the lecturer can see this message. So ultimately that, yeah, she can start at 9 o'clock. So I'll take 1 hour, right?
Okay, sir.
Right. So that's all from me today. And hope this is clear for you all. And so if you have any question, you can ask this one in next lecture, right? So I'll schedule the tutorials. Probably that we can do the one tutorial next Tuesday if Niroshan is available. If not, we will do it next time. Right.
Recording stopped.
So we are expecting to bring you to the university middle of December. And now we have scheduled the examination for your senior batch. This is a 1-2 examination. Once it finished, that we'll send them to home and we will bring it, right? So this is what we are planning right now. So before that, I have to finish all the lectures and tutorials. And once you come here, we will start the practicals and I will do only one revision lesson physically in the faculty, right? So this is what we are planning right now. Right. So hope everything is clear. And again, thank you very much for all the students. We have 80 students, so that's good. So I expect all the people to come to the lecture, right? That is really important. Under these circumstances, you have to gain the advantage which is available right now with these online lectures. Right. Okay. So then that's all, right? Thank you very much. And I have a meeting now, and my research assistants are waiting outside. So let me thank you to join again, and hope you have a nice time. Right. Thank you.